Hello guys, how are you today? So today I'll be explaining the chapter 1 introduction to organic chemistry. So 1.1 till 1.3 is super duper easy. It's like easy peasy lemon squeezy. But then 1.4 is like, I don't know. It's like the biggest drop I've ever seen. It's a nice chapter, and in my opinion, it's a bit difficult, but hopefully we'll be able to get through it. But let's start anyways with the first question. Identify the homologous series to which each compound belongs. So in AS chemistry, we learned about 9 homologous series, excluding alkanes, because alkanes are not like homologous series. They're all single covalent bonds. But homologous series, we learned 9, which are alkenes, halogenoalkenes, alcohol. My bad. Alcohols, ketones, aldehydes, carboxylic acid, esters, amines, and nitriles. In total, that is 9. So in this, they want us to identify the homologous series. Basically, in my opinion, if you don't see C, single bond, H, or like, if you don't see these three things, single bond, C, H, then you know that it's most likely what? It's most likely a homologous series. For example, we don't have a single bond here. It's a double bond. So when we have a double bond, what is the homologous series that comes into mind? It's alkenes. That means alkenes is what? Alkenes is our first homologous series over here. Now, for the second one, let us see. Look at this. It is C, double bond O, single bond O. So all of this is what? Is one homologous series, which is what? Which is esters, okay? So we didn't have single, we didn't have carbon, and we didn't have hydrogen only. So that means this is what? A homologous series. Then, OH over here. What is this? This is an alcohol. You guys are supposed to know by now, okay? Perfect. Look at this over here. We have a Br. What does it mean when we have a Br? That means it's a halogen. When we have a halogen, this is called what? It's called an halogenoalkane. Okay? Now let me scroll down. Look at this one over here. It's C single bond. C single bond H double bond O. Whenever we see C double bond O single bond H, this is what? This is an aldehyde. Perfect. And then here, what do we have? We have a nitrile. Perfect. So these are the homologous series. Hopefully you guys have them memorized. Alkenes, halogenoalkanes, alcohols, ketones, aldehydes, carboxylic acid, esters, amines, and nitriles. Now we go down. They said circle and name the functional group in each of the following structures. So these are skeletal structures. They want us to find their functional groups. First of all, here, this is what? This is an amine. Then we have C double bond OOH. That's COOH. That's a carboxyl from the carboxylic acid. And then here, what do we have? We have C double bond O, and this is what? This is a carbonyl. But carbonyl exists where? Carbonyl exists in ketones and aldehydes. Now, is it a ketone or is it an aldehyde? For sure it's a ketone. Why? Because an aldehyde is C double bond O single bond H, which we don't have over here. We have instead C double bond O single bond C. So, because we don't have over here, we can very simply say that this is what? This is a ketone. Perfect. We'll move on to question number 2. What does it say in question number 2? Draw the displayed formula of the following skeletal formulas. Very simply, let us draw the displayed formulas of the following skeletal formulas. First thing we do is we start by counting our carbons. We have 1, 2, 3, 4, 5, and 6 carbons. Now, these are the carbons where in the main branch, okay? So we need to put 6 carbons in the main branch. 1, 2, 3, 4, 5, and 6, okay? Now, if you notice, in between the third and the fourth one, there's a double bond. So we need to put a double bond over here. And the rest are all what? They're all single bonded to each other. Now, on the fourth carbon, we have what? We have a methyl, right? Which is CH3. That means on the fourth carbon, which is this one over here, we will draw a single bond. We will put a C over here. And we will add what? We will add H, H, and H. Perfect. Now, on the second carbon, we have an OH functional group. So we'll put O and then H. And now that there's nothing else to do, we will do what? We'll replace everything else by what? We'll replace everything else by hydrogen, okay? So hydrogen, 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 and hydrogen. So this is the displayed formula of the skeletal formula. Let us move down now to this one over here. We need to do the exact same process. So on our skeleton, or like on the backbone of this, we count how many carbons do we have? We have in total 6 carbons. So we will write 1, 2, 3, 4, 5, and 6 carbons. Perfect. Now on the, let's say this is the second carbon. On the second carbon, what do we have? We have the carbonyl group, which is C double bond O, okay? Then what do we also have? We have on the third carbon, we have what we have a methyl. And also on the fourth one, we have a methyl. That means on the third carbon after this, we can go down and we can put our methyl here. And then on the fourth one, we can do the exact same thing, but upwards. And then, since there's nothing else to add for the rest, what do we do? We will put the hydrogens, okay? So this is what it is supposed to look like. So that's it for this one. Now we'll move on to the last one. Again, what do? We will count, first of all of the number of carbons in the skeleton or the base of our structure, which in this scenario is 4. So we have 1, 2, 3, and 4 carbons, right? Now, on the third carbon, right? Let's say it's this carbon over here. We have what? We have a carbonyl group, which is double bond O. Then on the last carbon, we have OH. Then on the second carbon, we have a methyl, CH3. Now, what does it mean? This means for the rest, we need to add what? We need to add the hydrogen. Remember, each carbon does 4 bonds. That means hydrogen, hydrogen, hydrogen. This is how many bonds? 3 bonds. That means we have an extra hydrogen here. This is already 4 bonds. This is 2 bonds, so we need hydrogen up, hydrogen down. And that's it. This is what our structure looks like. Perfect. Now we go here. My bad, excuse me. Now we go here. Give the molecular formula of the following compounds. So they want us to find the molecular formula of these compounds. So let us start. First of all, what do? First of all, we, in my opinion, it would be better to do what? It would be better to graph it, just like how we did above. It does take time, but it's more accurate. So we start. How many carbons do we have? 1, 2, 3, 4, and 5 carbons. So 1, 2, 3, 4, and 5 carbons. There's no double bonds between them. Then, on this carbon over here, we have double bond O. And what does it mean? It means for the rest, we will put hydrogen. And each carbon makes 4 bonds. This already makes 4. That means it does not take any more. So now, what do we need to do? The only thing we need to do is to count. So we have how many carbons? We have 5 carbons, C5. H1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. H10, and how many O's do we have? We only have 1 O. So this is the molecular formula, C5H10O. Same thing for this one. Let us do this one. 1, 2, 3, 4 carbons, right? So 1, 2, 3, double bond, 4. So now, what do we notice as well? We notice that on this carbon, we have an OH. So what does it mean? This means for the rest of the carbons, we need to put hydrogen. Remember that each carbon makes 4 bonds. This makes 4 already, and this makes 4 as well. So H, 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 and H. So now what do? We need to count the number of carbons that we have. That's C4, H, 1, 2, 3, 4, 5, 6, 7, and 8. O. Perfect. We move on to this one. This one is very important. Let's count how many carbons do we have. 1, 2, 3, 4, 5, and 6 carbons. Right, let's draw it like this. 1, leave a gap. 2, leave a gap. 3, leave a gap. 4, 5, and 6, right? And then we have here what we have here, OH. Now, remember, we have carbon here, carbon here, carbon, 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 and carbon here. And remember that each carbon makes 4 bonds. That means this carbon would be bonded to an H because it's like already 3, so plus 1 more, that's gonna be 4. This has 2 bonds. So it needs how many hydrogens? It needs 2 more hydrogens. This also has 2 bonds, so it needs 2 more hydrogens. Also 2 bonds, so it needs 2 more hydrogens. Why 2 more hydrogens? So we can have 4 bonds then. Same scenario here and same scenario here. So now that we have everything, we'll be able to do what? We'll be able to count. So we have 1, 2, 3, 4, 5, 6 carbons, C6. How many H's do we have? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11, 12. Each 12 O. Perfect. So that is it for this one. Now, is this the last one? Yeah, perfect. This one is the last one. Let us do this as well. Let us draw it as well. So 1, 2, 3, 4, 5. And then we have a double bond over here. So remember, carbon, 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 carbon. This carbon already has 4 bonds. This has 2, so you add H2, 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 and H2. So the final answer for this one is supposed to be C5H8O. And yeah, this is the scenario. Perfect. So now we move on to part C. Here, we need to draw what? We need to draw the structural formula of butane 1-ol. First of all, butane is the number of carbons. 1 is the position of the functional group. And ol is the functional group. So it's an alcohol, that means it's a hydroxide, right? So let us draw the structural formula. It's gonna be C. That means we have 4 C's, right? So 1, 2, 3, and 4. And remember that each of the C's has what? Has 4 bonds. So this C is already bonded to this C, this C is already bonded to this C, this C is already bonded to this C, if that helps, of course. So 1 bond is gone. How many bonds remain? 3 more bonds remain, so we substituted by H3. Here, this is 2 bonds, right? So 2 bonds are gone. How do we substitute it? By H2, right? Because 2, we need 4, that's 2 more. This is again 2 bonds, so what do? We remove these and we put instead of it H2. And this is a single bond. How do we fix that? We fix that by inputting 2 more hydrogens, and there's one more thing we need to add, which is the OH. Remember that the carbon here will only bond to the oxygen, not the hydrogen. So it will bond 2 hydrogens here, like this, hydrogen, hydrogen, and OH. So like this, it would have what? It would have 4 bonds. That is why we say CH2OH. So this is the final structural formula of the following. Perfect, perfect. Pentene, very simply, not Pantene like the brand, no, pentene. Pent is the number of carbons that we have, which is what? Which is 5. Ene is the functional group. It's an alkene, that means it has C double bond C. So we need to write 5, 1, 2, 3, 4, and 5. Notice how it did not say pent 3-ene. If it said pent 3-ene, then we know where the double bond will be, which is on 3. But it did not say pent 3-ene. It didn't say anything. It's just like pentene. So we directly assume that it's what? That it's pent 1-ene. And when it's pent 1-ene, you can choose either here to put it. So this will be like this, and then the rest are all single bond. That means this already has 2 bonds, right? So it's gonna be CH2 left. Right, this has 3 bonds, so CH only left, right, because 4 minus 3 is 1. This has 2, 4 minus 2 is 2. This has 2, 4 minus 2 is 2. And this has only 1, so 4 minus 1, that's gonna be 3. So this is what it's supposed to look like. And don't forget the double bond wherever you put it. So CH2, CH, CH2, CH2, CH3. This is what it's supposed to look like. Perfect. 3. A compound with an empirical formula of CH has a molecular mass of 78. What is its molecular formula? How do we find its molecular formula, knowing we have its empirical formula? Very simply, we need to find the number n. How do we find the number n? It's the molecular mass divided by the empirical mass, which is CH, which is 12. My bad, 12 plus 1. That's going to be 13. I don't know why I needed the calculator for that. So then, 78 divided by 13, that's going to be 6. That means n is 6. That means the molecular formula is going to be C6H6, right? Now draw the skeletal structure of this compound. C6H6 reminds us of benzene, and benzene is what is cyclic. So how do we draw anything that's cyclic? We start. How many carbons does it have? 6. So it's going to be 1, 2, 3, 4, 5, and 6, right? So now we put them C, 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 and C. And H6, what does this mean? This means that there are only 6 hydrogens, right? So let's say we gave each one CH. So CH, 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 and CH. But now it won't add up. Why? Because this carbon over here has, with the H, 3 bonds. And carbon needs 4 bonds. Same with this carbon over here. So what do? We put a double bond over here. Okay, but now we can't put a double bond over here, because if we put a double bond over here, what's gonna happen? It's gonna be that this over here has 5 bonds, which is impossible. So that's why we can put it over here. Actually, not over there, over here. And then last but not least, we can't put it here, so where do we put it? We put it here. And just like that, this is what the cyclic benzene looks like. And of course, don't forget that benzene can change the double bonds. Like, they're always turning and shifting and changing between these. So this is the skeletal structure of benzene. Okay? Oh, by the way, you don't draw it like this in the exam with the CH. You just draw it like this. You draw 1, 2, 3, 4, 5, and 6. You draw it like this, okay? Without any carbons, without any hydrogen. The only thing that you add extra is if it's O or N or anything like that. So that is it for section 1.1. We move on to section 1.2. What does it say in section 1.2? In section 1.2 it says, draw 2 cyclic compounds with the molecular formula C6H12O. How would that look like? First of all, we have 6 carbons. So you have to draw 6 carbons, right? 1, 2, 3, 4, 5, and 6. I know it's not perfect. I can never draw it perfect, actually. So 1, 2, 3, 4, 5, and 6. Okay? Something like this, yeah? 6 carbons. We also have how many hydrogens? We have 12 hydrogens, right? So we have carbon here, carbon here, carbon here, carbon here, carbon here, and carbon here, right? So then we know that each carbon should have what? Should have 4 bonds. That means this can be H2, 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 and H2. But then we stop here for a second. Remember that we also need to put O. So we can say that this is CH. Now it has 3 bonds. Then we do another bond and we put OH. And just like that, it has 4 bonds and we satisfy what we satisfy, C6H12O. Now, of course, you're not going to put the C and H's on the formula. Your actual formula is supposed to look like this. Okay? Now, another one we could draw looks like this. Let me think. It looks like this. We draw 1, 2, 3, 4. Actually, wait, let me erase this so I have more space. We draw 1, 2, 3, 4, 5, and like this. Now, we will put an O over here. Let's say we put an O over here. Right? So how many carbons did we use? We used 1, 2, 3, 4, and 5 carbons. That means we're still missing 1 carbon. We could just do like this, and this is our 6th carbon. All right, now let us check to see if it satisfies H12. So this is oxygen, and this is 3 bonds. That means it just needs 1 H. 2 bonds, so H2. 2 bonds, so H2, H2, H2. Now here it's 1 bond, so it's going to be CH3. Now let's add them all together. 3 plus 1 plus 2 plus 2 plus 2 plus 2. That's going to give us what? That's going to give us 12. That means what? That means it's a correct answer. Now part B. Draw 1 branch compound with the molecular formula of C6H14. So let us just like draw a knee with C6H14 and it needs to be branched. What does it mean? Let's just draw C6H14. We start with C, 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 and C. That's 6 carbons. We do like this. And then for each one, what do? We put the hydrogen. So in total, it's going to be what? 6 carbons. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14 hydrogens. So this is not what they want from us. They want it to be branched. So what do? We could, for example, we could break off this part over here, right? We can say bye-bye to it. And we can put it where we can put it on this carbon over here, right? If we do end up putting it on this carbon, let us see what happens. Like this, it's fulfilling what? It's fulfilling 4 bonds. Perfect. But this is only fulfilling 2 bonds. So how do we make it 4? Because it's 1 bond over here. We just make 3 hydrogen. Perfect. That means the rest are all what? The rest are all of them being hydrogen. Now, this is a branch structure. How do we know? Because we have 6 C's, 1, 2, 3, 4, 5, and 6. And if you add all of the hydrogen in total, it's going to be what? It's going to be 14. Now, if you wanted to draw it, we could be like this. If you want to draw the skeleton, it will be carbon, 2, 3, 4, and 5 carbons, right? And then on the second carbon, what do we have? We have a methyl. So this is what it would look like in the skeletal formula. We move on to question number 5. Okay, so now we came to what? The naming of these compounds. So what do we start with? We start with this one, let's say. Yeah. So what do we do first of all? First of all, we see if there are any functional groups. So first step is to look for functional groups. If we don't see any functional groups, then we start by counting methyl. So we have methyl over here and the methyl over here. Now, we have 2 methyls. So what do we say? We say dimethyl. Di means 2. Methyl is the compound that we have, right? Now, where are they located? We always take the closest terminal carbon, which is here, and we count 1, 2, 1 carbon, 2 carbon, 3 carbon, 4 carbon, and 5 carbon. So they are located at which 2 positions? At positions 2 and 3. So now it's 2, 3 dimethyl. Now what do? We count the number of carbons in the compound, and we add at the end of it ane. So we have 5 carbons, and that's going to be pent, and then ane. So 2, 3 dimethyl pentane. Perfect. Now we'll move on to part B. What does it say in part B? Oh, we have 1, 2, 3, 4, 5, and 6 carbons in the main. So how many carbons do we have in the main? That is 6. So that's going to be hexane, right? Now, because it's closed, we call this cyclo. So it's going to be cyclohexane, right? Now we come here. Okay, what's this position? Let's call this position 1, right? Now, in position 1, what do we have? We have 1, 2 carbons that are branched out. What do we call 2 carbons that are branched out? We call them ethyl. Now, how many ethyls do we have? We have 2 ethyls. So, diethyl, okay? And which position are they located? They are located on 1, 1. So, it's 1, 1, dash, don't forget the dash, diethyl cyclohexane, okay? So now we go to the next one. First thing we start with is if we have any functional group. What's our functional group? It is what? It is the alkyl. Perfect. Now what do? We see if there's any branches. We have branches, and they are both what? They are both methyl, right? Now, what is the position? We start counting from the closest carbon to the functional group. What's the closest carbon to the functional group? In my opinion, it's this one. So 1, 2, 3, 4, and 5. So their positions are at carbon number 2 and carbon number 4, and then we will put a dash. Now, how many methyls do we have? We have 2 methyls, so that's 2, 4 dimethyl. Now, how many carbons do we have in the main skeleton? That's gonna be 5, so that's pent. Okay, so 2, 4 dimethyl pent. Now, where is the functional group located, and which carbon is it located? It's located in carbon number 2. So it's pent dash 2 ene. Okay, so 2, 4 dimethyl pent 2 ene. We move on to part D. What does it say in part D? What do we say first of all? We see if we have any functional group. Yes, that means it's an alcohol. Okay. Now what do? We see if there's any branches. We have a branch over here, and this is what? This is methyl. What's the position of methyl with respect to the functional group? Always you take with respect to the functional group. We have 1, 2, 3, 4, and 5. So methyl is in which group? In which carbon? Sorry, it's in carbon 4. So 4 dash methyl. Now, how many carbons do we have in the main skeleton? We have 5 carbons in the main skeleton. So that's pentane. Okay, and now we need to see on which carbon is the functional group located. It's located on the second carbon. That means pentan-2 all. That's it for part D. Is there part E? Yeah, there's part E and part F and G and H. What does it say in part E? In part E, it says, okay, now we move on to E. Now, what do we do first of all? We see if there's any functional group. Yes, we have a functional group. It's C double bond O, single bond O. So this is what? This is an ester, okay? How do we name an ester? Very simply, we'll divide it here in this position, right? All of the carbons before, so that's 1, 2, 3, and 4, they are what? They are but, okay, butan, and we don't forget to add O8. So butanoate. Perfect. Now, on the second side with the single bond O, so with the side with the double bond O, it's always the number of carbons with an O8. Then, the side with the single bond O, it's always the number of carbons with eel, so it's gonna be ethyl. Now, how do you name it? You always name it starting with the eel, then the anoate, so it will be ethyl butanoate. Okay, perfect. We'll move on to part E. What is this? First of all, we need to find any of the functional group. Actually, here we have a ketone because it's C double bond O with a group here and a different group here. So this is what? This is a ketone. How do we name a ketone? First things first, we need to see if we have any branches. We do have a branch over here. So this is methyl. And what is its position with respect to the ketone? So this is carbon 1, 2, 3, 4, and 5. So this is, actually it could be either 4 or it could be 1, 2, 3, 4, and 5. As you can see, it's the same either way. So it's better to choose what? It's better to choose the smaller number, so 2. So it's 2-methyl, 2-methyl. How many carbons do we have here? We have 5 carbons, so pentan. Now, very important, what's the position of the functional group? 3 and then on. So 2-methyl, pentan, 3 on. We move on to F. Now, what do we do over here? We see the functional group. This is an amine. So how do we name an amine? Actually, very, very important. Whenever we name an amine, okay, because it starts with an A, and alphabetically, we usually name everything in alphabetic order. So like A, B, C, D, etc. You know, because amine starts with an A, we're gonna start with it, right? So we're gonna start with, first of all, amine. On which carbon it is? We have 1, 2, 3, 4, 5 carbons, right? So it's on usually the first carbon, which is preferable. So it's gonna be 1-amino, okay? Now we go to the branch. So this is what? This is 1, 2, 3, 4, 5. So this is -2-methyl. Okay, now what do? We count the number of carbons in this, which is 5. So pent, and then because they're all single bond, we will say ane. So 1-amino, 2-methyl, pentane. That's it for this one. Now we move on to part H. This is what? This is a nitrile. How do we name nitrile? Again, alphabetical order. So first of all, we will see any branches. In this case, we have ethyl. What's the position of ethyl? Actually, it is 1, 2, 3, 4, 5 carbons. So 1, 2, 3, 4. Or no, sorry, my bad. I forgot to include that carbon. 1, 2, 3, 4, 5, and 6. So we start in with alphabetical order, of course. All right. So the first thing we're gonna put is ethyl. Now ethyl is on the 4th carbon, so 4-ethyl. Okay. Now, how many carbons are there in the full skeleton? We have 6 carbons, so that's gonna be hex. Okay, and they're all single bond, so we'll say hexane. And then last thing we put is what? Is nitrile. So 4-ethyl, hexane, nitrile. That's it for the naming. Now we move on to section 1.3, which is small, and then 1.4. Oh my goodness, 1.4. It's not too long, but at the same time, it's not that easy. So we will go to 1.3, okay? A structure of an organic molecule is shown below. 1.3 talks about pi and sigma bonds. They told us to say whether it's sp, sp2 or sp3 hybridization? We know that, first of all, if it's triple bond, then it's sp. If it's double bond, it's sp2. And if it's a single bond, it's sp3. Okay? So from AH, because it's what? Because it is a triple bond, we will say that this is sp hybridization. And II, part B, because it's a single bond, we will say that this is sp3 hybridization. Part C, oh my goodness, they disappeared. It's fine. So this is sp3. Part C, because it's a double bond, it's going to be what? It's going to be sp2 hybridization. Right? Now, in part B, it says they want the bond angle. What should you remember? You should remember that the bond angle in between triple bond is what? Is 180 degrees. The bond angle in between double bond is 120 degrees. And the bond angle between a single bond is 109.5 degrees. So these are very, very, very important. So they're asking us for the bond angle of 1, 2, and 3. 1 has a triple bond, so it's 180 degrees. Sorry, A, B, and C. B is single bond, so it's going to be 109.5 degrees. And C is what? C is a double bond, so it's going to be 120 degrees. So 180, 109.5, and 120 degrees. Question number 7. How many carbons are... Oh, did we finish this? Oh, no, sorry, my bad. Part C. Fill in the blanks with pi, sigma, or pi and sigma. They want the type of covalent bonds. So let's go up. When we have triple bond, okay? Always the bottom one is sigma, and then the top two are pi. When we have double bond, the double one is sigma, the top one is pi. And when we have single bond, it's only gonna be sigma, okay? That means for A, because we have triple, that means we will have what? We will have sigma and pi. Part B, because we only have single, we're only gonna have sigma. And for part C, because we have double, we're gonna have what? Sigma and pi. Perfect. Now we can move on to question number 7. How many carbons are coplanar in the following compound? Okay, now how do we know if something is in the same plane or coplanar? Coplanar means in the same plane. We have two conditions. The first condition is that it needs to be either sp2 or sp hybridized, okay, meaning that it has what? It has pi bondings. Actually, our second condition is that it has pi bondings, but like the whole idea is that sp2 sp having pi bonds means that it's gonna be what? There's a possibility of it being coplanar. So now we start. Let's see the bond. This is not what? This is not sp2 sp. This is sp2. We consider it. Not sp2 sp, not sp2 sp. So the only thing we'll be working with is this double bond, which is sp2. Now, for sure in the double bond, we have this carbon and this carbon, which are already planar, right? And in the sp2 sp hybridization, all the molecules that are attached to the main carbons, right? They are what? They are going to be coplanar. What does this mean? This means this hydrogen attached to the carbon is going to be coplanar. But they're asking how many carbons, so we're going to disregard all of the hydrogens, okay? So now, what do? We're going to take this carbon because it's directly attached to this carbon over here. So now, how many coplanar carbons do we have? 3. And this carbon as well, because we have what? Because it's directly attached to this carbon over here. So this means this carbon is not coplanar. Perfect. Now we move on to part B. Add the wedges and dashes for the hydrogens on the following compound. Okay, so they want us to add the wedges and the dashes for the hydrogens on the following compounds. Wedges and dashes means that it's in front of the plane. Dashes means it's behind of the plane. That doesn't mean that they are coplanar. So what does this mean? This means immediately we see anything coplanar, we will eliminate it. So what does coplanar mean? We need to find sp2, sp, or pi bonding. We start. No site of sp2, sp. Here we go. We have sp2. So what does this mean? This means that this carbon over here and this carbon over here are coplanar. And anything directly attached to them, meaning this carbon over here, okay? This hydrogen over here, this hydrogen and this hydrogen, they are also what? They are all coplanar as well. So they're not gonna be what? In front and behind. So that leaves us with 1, 2, and 3 areas for us to draw wedges and dashes. Now you just choose anything random. You can say, okay, By the way, what are the conditions for wedges and dashes? Wedges, dashes, and coplanar. For the coplanar, if carbon is bonded to another carbon, immediately they are what? They are coplanar. Then, we need another atom, whether carbon or something else, to be what? To be also in the plane. So it's going to be hydrogen. So what does it mean? Carbon directly bonded to carbon is already coplanar. But there's also something else, another atom, which needs to be what? Which needs to be coplanar. Okay? This is something very important to know. So what does this mean? This means if we choose this, right, we will have already this carbon attached to it, which is coplanar for sure. Now we choose one hydrogen. Okay, we're going to say that this is coplanar. Then we choose another hydrogen, we will say, okay, we're gonna give it a wedge. And then another hydrogen, we say, okay, I'm gonna give it some dashes. Same thing over here. We have another carbon directly attached to it, and another carbon directly attached to it. So directly we have what? We have two carbons that are attached to it. So we said we need two to be coplanar with the central carbon. Okay, that means that we can give this one a dash, and we can give this one what? A wedge. Now, for this one over here, we have one carbon already, another carbon already. So directly, what do we say? We say this one we can give it dashes, and this one we can give it what? We can give it a wedge. So it's supposed to look like this. Perfect. We finished 1.3. Now we reached 1.4. I'm gonna take like a small break. I'll be right back. Okay, now for section 1.4, isomerism. For the molecular formula C4H10O. So personally, I would like to draw it like this, C4. And then OH, H, 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 H. And just like that, what do we have? We have C4H10O, okay? So now let us draw the chain isomer. Of course, it needs to be in the skeletal format. So it's gonna be what? It's gonna be one like this. So this is how it looks like in the skeletal format. So this is the first chain isomer. Now let's say we get rid of this and we put it over here. How would it look like? It would look like this. So this is what the second chain isomer looks like. So just like that, we finished what? We finished the chain isomers. Let's now move on to the position isomers. Position isomers means that we're changing the position of OH. So now let us change the position of OH. So we said maybe we could change OH from here. We'll put it as H over here, and we could put it over here. If that's the scenario, my bad, I dropped my pen. If that's the scenario, then if we drew it, it would look like this. It would look like 1, 2, 3, 4. Okay, 4 carbons. And then on the second carbon, we have an OH group, right? And of course, we can take how it was originally. How was it originally? Originally, it was like this. It was 1, 2, 3, and 4 carbons with what? With OH. So just like that, we finished what? We finished the position isomers. Now the last thing is the functional group isomers. So what can we do with this? We can say that again, we could draw it as it is like right now. We can do it 1, 2, 3, 4, and then OH. All right, this is the first functional group isomer. Then what if we moved the functional group, and where did we put it? We put it, let's say, over here. We put O, right? We said that we put O over here, and then we get rid of the H on top, and then we have what? We have a CH3. So let's say we moved the OH, right? Actually, we didn't move the OH. We moved the O and we moved it inside. So this is called what? This is called functional group isomerism, meaning we're changing the functional group, right? So now let's count. How many carbons do we have? We have 4 carbons. How many hydrogens do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. H10 and 1 single O. So this also works as well. So we could draw it like this. We could draw it as 1, 2, 3, O, and then what? And then like this. So this is the second functional group isomer. After that, we'll move on to question number 9. They said, classify each pair as what? As stereoisomers or as structural isomers. Okay, so structural isomers, okay, what's the difference between structural and stereo? Structural isomers have the same molecular formula, same exact molecular formula, but a different arrangement of atoms. Whereas stereoisomers, on the other hand, stereoisomers have the same molecular formula, but they have a different spatial arrangement, meaning geometrically shaped, different. Let's take these as an example, right? So we need to see which one is structural and which one is stereoisomer. So we start with this one. Do we change their spatial arrangement or just the arrangement of atoms? In fact, no, we're only change in arrangement, only. Arrangement of atoms, because we did not change the spatial arrangement. And because of this, what happens? Their name changes, right? So, because a very big hint to help us in knowing whether it's structural or stereo, is that if their name changes. If their name changes, then directly it's structural. And if their name stays the same, then directly it's what? It's stereo. Okay? For example, let's name these. For example, this is 1, 2, 3, 4 carbons, right? And here's the double bond. And here's the methyl, right? So it's gonna be what? It's gonna be 3 methyl. Or actually even better, 2 methyl, but, 2 ene. This is the first name. For the second name, for this one, if we were to name it, it would be 1, 2, 3, 4 carbons, right? And then we also have methyl as well, but now methyl is where? It's 1, 2, 3. Now methyl is 3, so it becomes 3 methyl, but, 1 ene. So as you can see, their names changed. Because their names changed, we can say that they are what? They are structural isomers. Whereas over here, what can we say for the stereoisomers? Let's name this one. This one, if you name it, it's but, 2 ene. Same thing with this one. If you name it, it's but, 2 ene. As you can see, they both have what? They both have the same name, but the only difference is how their spatial arrangement is, how their structure is. So because of this, we say that they are what? They are stereoisomers. Okay? We move on to question number 10. What does it say? It says, how many optical isomers are there for naproxen? Okay, so how do we know about optical isomers? What are the 2 conditions for optical isomers? First condition is that we need to find a chiral center. After that, we need to make sure what? We need to make sure that they are enantiomers, meaning they are non-superimposable. What does enantiomers mean? Enantiomers means that when you draw the axis of symmetry, for example, you draw it like this, right? And you fold them on top of each other, or like you flip them, then they would not be symmetrical, okay? So in order for it to be optical isomers, okay, first of all, we need to find the chiral center. Then if we drew a line in between and like we folded them and they were symmetrical, or like we did a mirror image and they are symmetrical to each other, then we will say these are not optical isomers. But if they're asymmetrical to each other, then they are what? They are optical isomers. So here we need to find the chiral center. Yeah, I forgot to mention, what does chiral center mean? Chiral center, it is a carbon that has 4 different groups attached. Okay? And of course, we need to know that it's 4 single bond, meaning it's sp3 hybridized. So over here, we're looking for what? We're looking for a chiral center. The chiral center should have what? It should be carbon, first of all, and it has 4 different groups surrounding it. That means, first of all, it needs to be an sp3 bond, right? So we cross out anything that is not sp3, that is not a single bond. This we don't take it because it's with oxygen. We don't take this because it's with oxygen. And we don't take this because it's with oxygen, okay? So now we lowered all of the the possibilities that we have, okay? Now, we need to say this one. This one We can't take it because there's a double bond. Okay? It's like all of this, we can't take it because there's a double bond. And same here, we cannot take all of this because it's doubly bonded. So we're left with what? We're left with either here, but here as well there's a double bond, so we can't take it. So then we're left with this position over here. Let's look at this position over here. We will see the different types of groups that it has attached to it. First of all, we have all of this from the side. From the top we have CH3. From the bottom we have hydrogen, and then we have all of this from the other side. As you can see, every single one is different. So it has 4 different groups attached. That means this is for sure a chiral center. Now this is the only chiral center that we found. So as long as there is a single chiral center, right, then we'll be able to find what? We'll be able to find the number of optical isomers. How do we do that? Very simply, biologically speaking. We have one chiral center, right? How many images will it produce? It will produce, of course, if we're doing the mirror image like this, it will produce another image. So in reality, it will have 2 images. That means 2 optical isomers. Actually, there's an equation. Thanks to my friend for telling me this. There's an equation in order to find out how many optical isomers there are. You take 2 to the power of the number of chiral centers. So number of chiral centers. Right? So for example, in this scenario, we have one chiral center. It will be 2 to the power of 1. So 2 optical isomers. This only applies for optical isomers, by the way, okay? Now we move on to part B. It says in part B, how many geometrical isomers are possible for the following compound? When we say geometrical isomers, it means we're talking about what? About cis and trans. Cis and trans isomers. Now, what are the conditions for cis and trans? First of all, for cis and trans, we need to have what? We need to have prevention of rotation. So prevention of rotation. That is why it's preferable for us to have what? A C double bond C. Okay? So the C double bond C, okay, will prevent free rotation. Now, the second condition is that each carbon of the double bond must have 2 different constituents, meaning this carbon and this carbon and this carbon and this carbon will have different constituents. So this carbon will have and this carbon will have. For example, we'll say this is A, okay? This carbon cannot have A. If this carbon also has A, then this is what? This is not a cis or trans. Okay, so this carbon can only have A and B. This carbon can also have only A and B. If it is like this, then we say that this is what? That this is a cis. Okay? However, let's say that we didn't put it like this. We said that this can have A and B and this can have B and A. When it's like this, we call this trans. So the only difference between cis and trans is the location of the different constituents. For example, A and B, if they are on the same side, then this is what? This is cis. Okay? However, if they are on opposite sides, like here, then they are what? Then they are trans. Okay, so in this scenario, what do we need to do? We need to, first of all, we don't take any single bond, we focus on the double bonds. So we take this double bond, this is a double bond, first of all, double bond and double bond. So these are the things we will be focusing on. Now, let us see. We will see. First of all, for this one, let's focus on this double bond over here. We have a carbon over here, CH2 actually. We have C double bond C over here. We have CH2 over here. And then we will have a hydrogen over here. But however, we notice something. We notice that this is what? This is a ring, right? But this ring, okay, is locked. What does this mean? Usually, if you remember, for example, in the benzene example, okay, horrible drawing, we would draw it like this. Why? Because there were double bonds here and here and here. And these double bonds would shift and alternate, meaning that their positions will change. There's different possibilities for positions. But in this scenario over here, what do we have? We have that it is locked and fixed. So because it is locked and fixed, there will be no other possibility, right? So due to this, we will see that there is no cis and no trans isomers over here. So we just got rid of which one? Of this one. It does not have cis or trans. Now let's focus on this one. This carbon has all of this hydrogen. This carbon has this and all of this. So as you can see, it has what? It has two on opposite sides, right? So the two different carbons have hydrogens that are what? That are diagonal to each other. So what do we call this type of bond? We call this a trans bond. Okay, and now last but not least for this one over here. Now finally for this one over here, as you can see, it's C single bond C. But the only issue is that this C, if you remove the H2, it would be H up and H down. So the H up and H down will basically like not make it or not let it be an isomer. Now, again, this is a geometrical equation, okay? Like an equation. To find the number of geometrical isomers, if it is what? If it is an alkene, that means you have C double bond C. In this scenario, we do have C double bond C. So because we have C double bond C, what can we say? We can say that it's 2 to the power of n, where n is the number of double bonds that can be what? That can be cis and trans. So in this scenario, it's going to be 2 to the power of 1, which is what? Which is 2. So that is why this will have 2 geometrical isomers. We move on to part C. What does it say in part C? How many stereoisomers are possible for this compound? Remember, we said when we're dealing with stereoisomers, that means it can be either what? It can be either geometric or geometrical isomers, or it can be what? Or it can be optical isomers. So what does this mean? This means we need to be looking for a chiral center for the optical, and we'll need to be looking for what? We'll need to be looking for C double bond C for what? For the geometrical. So I start over here. I found C double bond C. Let me see. Will this be a trans or cis or geometrical isomer? Let us see. You have like this. Yeah, they are opposite to each other. But first, let us see the group. This carbon has 1, 2 group. This carbon has 1, 2 group. Perfect. So now that means these are what? These are trans isomers. Of course, trans isomers can also make cis isomers. So this is why we say 2 to the power of n, 2 to the power of a number of double bonds, right? So that means how many double bonds, how many isomers, geometrical isomers can this make? It can make 2 geometrical isomers. Now, this is in addition to what? This is in addition to the chiral center, which we need to find out. What's a chiral center? It's a chiral center that has 4 different groups attached. So let us see. If we took this as a chiral center, we have a carbon here, but we also have a carbon here and a carbon here. So definitely this is not a chiral center. Now, if we took this as a chiral center, there's a double bond, so we cannot take it because a chiral center is only single bonds. If we took this as a chiral center, let us see. We have 1 carbon here, 1 chlorine here, 1 hydrogen here, and what? And 1 CH3. So this is in total 4 different groups. So this is our chiral center because there's 4 different groups surrounding it. Now remember the equation for the chiral center. How do you find the number of optical isomers? 2 to the power of the number of chiral centers, which is 1, which is also 2. So that's going to be 2 plus 2, which is what? Which is 4 stereoisomers. Let me see. I think 11 is the last question. Perfect. 11G. Drug cortisone has the following structure. Cortisol exhibits optical isomers and has a number of chiral centers. So, which of the following, what is the name of 2 different optical isomers? They are enantiomers. What's the number of chiral centers in the cortisol molecule? We start here. First of all, we don't take anything with double bonds. So here, directly, we have hydrogen up, hydrogen down. 2 the same, we cancel it out. Same thing, hydrogen up, hydrogen down. 2 the same, we cancel it out. Now, we reached this point over here. What can we notice? In this point over here, we have this is 1. This is 1 group. This is all a second group. There is CH3, and don't forget the hydrogen bonded over here. So these are what? These are 4 different groups. That means this is our first chiral center. Now we continue, we move on. We come here, let us see. From here, we have all of this as our first group. Then all of this as our second group. Actually, my bad, my mistake. For the pink one, it has what? It has this is 1, okay? Hydrogen is another, okay? Then this is another, right? All of this is another one. And then last but not least, this is what? The 4th one. So as you can see, they're all different as well. Because they're all different, this just proves even more that this is what? This is a chiral center. Now, we move on to the next chiral center, which I believe is over here. So over here, again, the same exact scenario. We have another hydrogen, okay? And we have here, basically all of this. And then this. And then all of this. And we don't forget, last but not least, the hydrogen. So as you can see, they're all different groups. Because they're all different groups, this just makes it even more what? Makes it even more a chiral center. Now, the next one is over here. As you can see over here, we have 1. I think all of this is 1. Then we have 2, which is all of this. Then we have 3, which is this, and then we have 4, which is the hydrogen. So as you can see, they're all different groups. So of course, these are what? Of course, these are chiral. This is a chiral center. The next one is over here. So as you can see from here, it's 1, then 2, then 3, and then don't forget about the 4th one, which is what? Which is the hydrogen over here. So as you can see, these are what? These are 4 different groups. So this makes it what? This makes it a chiral center. Now the last one is over here. Why? Because very simply, as you can see, we have all of this in addition to this, in addition to all of this, in addition to the OH. So this is 4 different groups. So that makes it what? That makes it a chiral center. So in total, we have 6 chiral centers. So in the cortisol molecule, there are 6 chiral centers. We move on to part B. An organic molecule is 1,3-cyclobutane dicarboxylic acid. Its structure is shown below. So what can you see over here? What type of stereoisomer is exhibited in this molecule? Very simply, it's what? It's a geometrical isomerism. Why is that? Because we said geometrical isomerism is like this. It was that you have, if you were to draw it like this and fold it on top of each other, it would not be what? It would not be symmetrical. So because it's not symmetrical, then we say that it's a geometrical isomer. Now in part II, it says fill in the blanks with cis or trans to give the name of the isomer below. So because one is in front of the plane, one is behind the plane, directly we know that this is trans isomerism. So thank you guys for watching this video. I hope that it was a good one. I don't know, I felt like it was a bit off. So I hope you enjoyed the video, and thank you guys for watching.